Oh, by the way, the people who are in the meetings, Mike Beckich, forget Tim's last name, you know, Tappan, yeah, they were both in the meeting. And if you guys, why do I have the name? I need the mouse to power something. One of the things we talked about was LinkedIn. How many of you have, let me say, yeah, probably it's easier. Who does not have a LinkedIn account set up? Why not?
Like a personal or
Professional. LinkedIn, professional LinkedIn.
Have you talked to Dean regarding that? I brought it to attention that I think premium is something students should get.
You don't need premium. I don't have premium. I've been in LinkedIn since the day I started, almost within the first month.
I made the argument.
I paid for it occasionally for free, and I turned it off.
Hey. I think it's useful too.
It's not really, it's not a fun place. If people want to talk to you, after they see you, they will. You know.
I meant the messaging. You can reach out to people without having to be connected.
No, I think it's more important to connect through your connections. It's a stronger reference. So no, I would disagree that you need professional. If you're sales, yes, I would disagree. I would say you need to have it. But yes, you're selling yourselves, but no, you don't need it.
Okay.
So that's my opinion, but I'll be pretty strong on that opinion. So if you don't have one, you should have one. I really firmly believe that. I have one. I used to not link into students. I've changed that policy now. I link into you when I think you are doing good work and are committed to your degree. So if you haven't linked into me and you want to, link into me by all means. Putting together a LinkedIn profile is as much as writing a good resume. They're almost like one and the same. So you should have a good resume. I was just talking to my son about this because he won't listen to anything I tell him. But go to the Career Center and talk to them about your resume. I can't stress that enough either. Funny thing was when my son comes back, he was talking to Lockheed too. He's a graduate student here and he's working with the aerospace department. And he was talking to Lockheed on some project he's working on. And the recruiter was looking at his resume and went through all these things and like, Sean, I told you that too many times. Sometimes it's not when the dad or mom say it, it's when somebody else says it, right? If your parents do appreciate that statement, you will.
Did you speak to Tim?
Briefly, we were in the middle of the meetings. He had some ideas for us.
Yeah, I had spoken to him. He's like, oh, okay, I have some.
Yeah, we talked briefly.
Like, speak to.
Yeah, we talked briefly.
He mentioned he had something else he wanted to pursue and bring up to your
Yeah. We'll talk more about that. You can reach out to him more, and we can maybe set up a meeting to get his thoughts. Okay, almost there. So yes, we were on differential motion, and I believe we were still on lecture 5. And you all probably said, oh, I guess we're not having class today, right? He was here this morning, where did he go? I realized I didn't have my phone with me, I was eating lunch, I was in the back. We were having this great conversation, and I go, wait, that clock says 1 o'clock. I don't trust the clock to be quite honest with you, neither do you. I go, it could be 1:05. I should go look, because my phone was on the other side of the table. I went and looked at it, and I go, shit, it's 1:05. Late. My apologies. This is the wrong file. So my apologies. But presentations today, you guys did really good. That was one of the things they were talking about was presenting, having you guys practice presenting. I didn't tell them what we're doing in this class necessarily because I can't speak to the other ways it's taught. This is the way I teach the class because this is the things that I think are important coming from 20 years of R&D history. So that's really where my perspective is, but that doesn't mean every professor has their own opinions on how things should be taught. Sometimes they align more with others, other times they don't. So, sometimes you take somebody who's really, really, really hard, maybe that's me, and maybe take someone who's not really, really hard. I don't know. But I think you get out of what you put into it, like anything. You're looking for your ROI, and that's the important part. And I think many of you guys will agree with that. That's good academic maturity on your part. That's plugged in. Okay, here we are. Jacobian space. Jacob space. So again, we were talking on, I know we went through it, but I think that last slide, because I had the one open, we're on slide 19. I said, no, let's go ahead. We're going to rewrite that one up. So before I do, let's go back to this last idea. We were talking about Jacobians. And again, the Jacobian is really, it's like a transform because you're going from one space to the next, but it's really dealing with the differential changes in spaces. That's why we're taking the partial derivatives. Now the question is, we derived the Jacobian. If you remember, we did the derivative, versions of it. But and I said it's similar to the transforms, and you can say, well, transform converts from one space to the other. It does, but it doesn't take into account differential changes. And that's where the Jacobian does do that. So it is a space transformation, but it's more than just a transform. So it kind of like does everything. So if we look at the Jacobian space, let me go ahead and zoom in this a little bit more so I can see. We know that the number of columns is going to be equal to the number of joints, at least from a robotics perspective. It was funny, I was on Monday after class, I was talking to a colleague of mine who was working in Aero. He's actually a lecturer who's doing research with also with Dr. Mandari, and I talk about Jacobians of UAV. They go, it's really simple. He's like, I don't know, this is computer science. I'm just a computer science guy. So I said, Jacobians are just doing this, and we just got done lecturing. And it dawned on me, because I needed to explain this to you guys, you could do a Jacobian for anything. You could do a Jacobian for autonomous vehicles or for a quad drone, where you would have each one of these individual thrusts of each motor, right? We all know how the drones work. There are these four motors. Each one of these has its own thrusts. Based on its thrust, it's going to pivot this way, or this way, or this way, or this way, right? Does that not sound familiar? That center point right there could be the tip, and this could be each one of the thrusts. Velocity 1, 2, 3, 4. How does that position change? What is its velocity? Boom, that's Jacobian. Let's think of an autonomous vehicle that sits on the ground. So let's do an underwater one, because it's basically the same as an air one, right? Forward, up, down, left, it's the same thing. An autonomous ground vehicle. I'm moving forwards and reverse. I could have a thrust that's going to convert this rotational motion. I can define that through motor 1, motor 2, motor 3, motor 4. If I have 4 motors, it's 4 by, like my little Scout. Or maybe you've seen the observer vehicle that I've shown you guys, where you have front and aft drive and accrements. So you would have that controls, and you can articulate those velocities. Those velocities would translate into some other motion that you could describe. And then you realize Jacobians are everywhere. Not just in arms, but in ground vehicles, in air vehicles, and underwater vehicles, and anything that has motion, which is pretty much everything. Does that all make sense all of a sudden? So that being said, the number of columns is going to be equal to the number of joints. And we're talking about a manipulator in this case. So the number of columns, I'm just going to do a lot of abbreviation, is equal to, that's a L, the number of joints. And when I say joints, again, in a robot arm, it's that fixed joint. But it could be the number of things that move, the number of differential things, like theta dot 1, 2, 3, 4 for our quad example I just got done talking about, right? Theta 1, 2, 3, theta 3, theta 4. In a robot, theta 1, 2, 3, 4, 5, 6, for example. The joint vector has a number of rows as the number of joints. And that again is to allow us to construct and relate this N to M relationship. So if I have M joints, I could have N things that the end effector is doing, so that my Jacobians matrix size is going to be in my M coordinate. Does that all make sense so far? Okay. And so we know that we can define a position of the end effector by means of DH parameters. So again, we had T, the transform from joint 0 to joint 1. And by the way, the due date will be Friday night for sim, if you missed last whatever. Yeah.
It says we know we can.
We know we can define the position of the end effector by means of the DH parameters. Thank you. So we have the transform from 0 to 1. We have the transform from 1 to 2, the transform to 2 to 3. Like so, for example, in our planar robot arm that we talked about, we've got the relationship. Those are my little joints. And here's my end effector. So I've got this length L1, as you recall, and I've got, this is going to be frame 1, let's call this frame 0, or UCS. I've got frame 2 for this joint. I've got the end effector, or frame 3, right here. This is going to be L2, theta 1, and this is theta 2. It really kind of followed through from that continuum point. And so we learn that we can find that overall transform from our UCS to our end effector frame. That's the positional description of its relative to the neighboring joints, is what that means. And if we recall, we have the transform from 0 to 1. This is planar. You should be able to do this in your sleep by now. What would my transform be? I'm rotating about Z. So I'm going to get, is there any rotation that has an alpha twist in here?
No.
No. Okay, so that makes it easy right away. We always know we're doing Z, so it's going to be nothing more than the Z transform, right? So what do we have? We have cosine 1 minus sine 1, 0. The L doesn't exist yet. We're going to, the L is going to be the next one. So we got a pos, we got a cosine 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Done. Okay. And then T1 to 2 is cut and paste, except now we have a 1 in there. So I'm just going to say RZ, if that's okay with you all. And then I'm going to do L1, not 4. That's 3 lines to make a square. Y'all are never going to listen to that. 0, 0, 0, 1, 0, 0, 0, 1. And then to go, the transform from 2 to 3 is going to be nothing more than the identity matrix, so there's no more rotations. But we have to carry through our L2, 0, 0, and the 1, 0, 0, 0. And so we know what that is. We know those transforms, or at least we should know them very well. Now the question is, these are the T's. So the question becomes, how does that T go to a J? That's the question.
To a Jacobian.
How do we relate the transforms to the Jacobian? And it turns out, to do that, we look at R. We want to look at R. And that's what we were talking about today. But I want to kind of revisit the transforms in the planar arm, just in case we threw all that knowledge that we had away. Because again, we're trying to look at this velocity of this point as it moves along, say, some line, some trajectory.
Professor,
Yeah.
what is the is plus minus? Like and 2, 3? That.
This guy right here,
Uh-huh.
that's an I.
Oh,
Matrix.
Oh, okay.
So I had to rotate about Z matrix. I just did it shorthand because it's cosine minus sine minus cosine minus sine cosine.
Mm-hmm.
0, 0, 0, 0.
Yeah.
We know that one. We've arrived at a billion times. So I just wrote it in shorthand. But this is information that we can use, right? It incorporates the twist. It'll incorporate alpha in there. And so we can use that to help us figure out that relationship. So why do we use the Jacobian? Because the Jacobian allows us to find the joint velocities, as we saw from Coppelius. Okay, so these are the motors that we can command. So again, going back to the notion of the quad drone, I can control 4 motors. And from those 4 motors, I control the position, orientation, everything about that drone. I can write a Jacobian for it. I can do it for a fixed-wing aircraft. I can do it for a ground vehicle. I can do it for a swimming vehicle. I can do it for anything that's got motion that we're writing and it's translating or behaving in some space where we're commanding. If we think about an autonomous vehicle, for example, it's rolling on wheels, isn't it? We don't simply have a transport from here to here. We define the velocities. And if you guys have taken autonomous vehicles in fall, which you all should if you're still on campus, I can make sure you all do stay on campus. Don't do that. This is close to graduation. Don't even do it. But we see that we can use Jacobians for anything that's motion, but has control of that motion in a different space. We don't think of those 2 motors like the think of the observer vehicle that I have, the 6-wheel vehicle. It's got forward that can steer, back that can steer, and the forward and after the driver. So I have 4 degrees of freedom, or 3 degrees of freedom. I have back and forth, and I have left and right of each wheel. I could say I have 2.5 or 3 degrees. But I can relate that motion for those motors through the Jacobian to the velocity of that device. The same thing we can do for the robot arm. The motion of those motors, the velocity of those motors, result in this tip moving across in a line. That's the Jacobian. All right. Are we clear on Jacobians? So I do have more slides. Okay, I thought that was the last slide. So let's go ahead and talk about this R matrix and relate it to the S matrix. There's a little bit of linear algebra here. I know that some of you may not have had a lot of linear algebra. We are addressing that in the program where we're going to have you guys take linear algebras, your undergrad calculus, and teach you differential equations instead through the material. I don't know if you get this or not, so I'm going to give it to you anyways. Doesn't matter, you necessarily haven't had it. So if we look at the transform, we know that we're going to have a valid R matrix. And we know it's an orthonormal matrix. An orthonormal matrix means R equals R transpose equals 1, and also that the inverter, the inverse of R is equal to the transpose of R, right? That's the definition. We showed that. Now, what we're really doing is we want to take the derivative of R, don't we? Right, that's the rotation that we're talking about. So we want to know R dot. Okay. So we can show, because we know that R times R transform equals I. And if we want to take the derivative, what we will do, and this is where it's a little different, this is you just have to accept me on this one for right now. But we could say that the R dot, the derivative of the matrix, times the transform. And we're going to say we're going to call this S. And we're also going to then add this with R R transport. And that this is going to be, I'm sorry, this is a dot right there. This is going to be called S transport. And we're going to define this relationship of R dot times R transform. We're going to define as our matrix S. So these are all matrices. I'm going to skip the little brackets if that's okay with you all. I need a little pen to automatically bold the pen so it'll show me. I don't need to do this, do I? Are we all doing it?
No.
So this matrix S has a special name. It's going to be called the skew matrix. That's definition. We're going to need. So we also know a point P in frame A is equal to the rotation from A to B. It can be describing that point B through a rotation. Right? So we know that that point B is therefore equal to the inverse rotation from A to B, P and A.
Is it B2A?
And we're going to say this if B
So where does the negative 1 come from?
is the inverse. I don't know why that's disappeared. Unplug it, plug it. There we go. My apologies. So, whoops, if B is rotating, not rotated, it's rotating, so now we have a velocity, such that the rotation AB is not 0. We know that this guy here, we can simply say it's a way of representing A, that the point in A will be changing even if the point in B is constant. So let's think for just a second. The point in A can be changing, even though that point representation in B isn't changing. It could be constant because it's not moving. And so if we look at the velocity in the S matrix, and I'm paraphrasing the book, so please read the book on this. I'm summarizing what it's getting at. Is if we define that skew matrix as R dot RT, we also know then can say that, instead of saying no, we also can say, I repeated the top part of that slide on the next slide if you look at the source. That if my point is changing in A, then I have to have something changing in that rotation matrix of B, which may not be changing. All right? The rotation can change, causing the point to change in A, but B is not changing, using a statement from right here. But that's saying the same thing. Now we can substitute this P dot to be our velocity matrix in A. It is going to be the rotational rate of change from A to B.
Is that AW?
B.
Oh,
Times P. I have no idea what I'm writing. Let me tell you that is first. We have no problem. Okay, we do that. There we go. It's already on spring break.
it's red.
So anyways, this is point B. But we can substitute that for PB so that we're going to get our velocity in our A frame is going to be R dot A to B. But PB, we could simply say is going to be the rotation from A to B inverse, like we had on the other page, times P and A. Which right here we already defined because we know there's orthonormality in R, so that we can say that V, the velocity in A, is going to be that skew matrix from A to B times P and A. So I can relate the velocities in A through that skew matrix S for that position in A. And the way it looks is I'm going to have the structure. I'm not going to go through the derivation. It's in the book. It's not that hard, but it gets a little lengthy. We'll come back to this matrix more. But we can write it as omega z. So 0, omega z, omega y. Omega z 0 minus omega x. And all we're doing is taking this guy right here. So we're taking the transform of that times the dot of this. And this becomes, and just doing the r, so we don't have to worry about the x, the bottom row and that the vector. This becomes minus omega y, omega x, and 0. So this is equal to. So these are the individual rotational elements about those axes. These are the individual angular components that define axes. So given point A, or given point P in A and a rotation frame, we can look at the end effector velocity in Cartesian. So I'm going to go ahead and write that. Given a point A in P, so I have P in A, and a rotation frame, the end effector velocity will be in Cartesian space. That is, as it moves across, that's my Cartesian space. These are my angles, this is my rotational velocities. About axes. I think that's the end of that slide deck. I think I chopped this one up into half. I did. So that's the idea of where we're going to go. We're going to explore this a little bit more, but we're going to come back to this idea a little bit later. It's kind of like setting that up for a little bit. We'll come back to that. Is that okay? So we'll go to close that down and save it. Then we'll go to the next one, which is actually only like 14 slides. So we've introduced the idea of differential motion. We've introduced the idea of the Jacobian. And we've kind of had some discussion in this overall differential motion. We haven't really gone through that a whole lot, and we're going to come back to that, I promise. What we're going to talk about next is, the wrong slide again. Okay, well, I guess you get the already written out parts for whatever reason. Oh, it's just that slide. Okay, so I'm not going to read that. So let's go back here. So we're going to talk now. We're going to put a pause right here. We're going to talk about the idea of differential motions between frames, because that is what we're talking about, right? We know what frames are. So if we can describe the differential motions between frames, then we can relate thetas to the frame. And I can do all that. If I know all my frames, then I can stack everything up from my frames, my t's, to get to my differential motions. Everybody with me on that so far? Which we know fundamentally the end state is the Jacobian. Okay. So, you don't have to write anything unless you want to. So we talk about differential motions and translations. We're talking about the frame T, and we're going to decompose this into differential translation and differential rotation. So we're going to treat both of them separately. Okay. When we talk about differential translations, we're talking about the translations along dx, along dy, and along dz. So we're saying that this frame, as it's moving from here to here, I can describe that relationship as some differential amount. Again, really small delta t, right? We're not talking this d, this delta. We're talking the little delta, right? The infinitesimal amount, the calculus delta. You take that limit and it goes to 0. That's the infinitesimal amount we're talking about, because that's how we get velocity, right? Is differential motion. So we're talking about the fact that it's going to be moving along these axes of x, y, and z by some differential amount. That's differential translation. Differential rotation, on the other hand, is instead of rotating, instead of translating, we're going to do this rock or this rotation right here by this amount theta about some arbitrary point q. We don't really care where q is, versus some point q that we're going to rotate by. We're going to rotate by some differential amount of theta from that frame. So we're going to go from one frame to the next by some differential amount of theta. Is that fair? Just like we went from one point to another point along some linear axis, we're going to rotate about some point q in space by some theta d theta. Okay. And so in NICU, there's missing a delta x. We're using the delta x, delta y, delta z representation for the axes that we're rotating about. Now, you probably have all heard about these small angle approximations. Yes, no? The sign of delta x is essentially made close to delta x. So it's a small angle. It's just going to be some arbitrary small angle. And the cosine is going to be 1. Because it's a very small angle. Remember, delta x is a very, very, very small value. We just got done saying that. We said as the delta approaches 0, right? Infinitesimal amounts. Infinitesimal amount 0, cosine of 0 is a 1. And that's why we said sine of 0 is 0. So that's why we're going to get away with that statement right there, is assuming the small angle approximations. So we're going to use these this rotation matrices using the small angle approximations. Approximation, apparently, is the new way of spelling it. So that's the idea that we're going to do. So let's look at that. Let's look at constructing what these rotation rates look like. So we just got done talking about the frames, right? We talked about, we rotated about Z right here. And these are our rotational frames that we constructed about a month ago, right? So, that being said, I'm going to use a small angle approximation for each one of these. So if I do that small angle approximation for each one of these, then my rotation, x by delta x, is going to be, we're going to get 1, 0, 0, 0, 0, right? So we're looking at this one right here. So 1, 0, 0, 1, 0, 0. Okay? Cosine of theta, where this is now a very small angle, we go to what?
1.
1. Minus sine is going to go to what?
0.
Nope.
No. Oh, delta.
The minus delta x, right?
Oh, okay.
So I have a 0, 0. The sine is going to be delta x. Cosine is going to be 1. We're going to go ahead, that's the submatrix. We're going to carry through our 0, 0, 0, 1 and our 0, 0, 0, 1. We're going to get our overall. No translation. We're going to do translation separate. We're going to do rotations and then translations and squish them together like we did before we did translations. Is that fair? Again, we carry the 1 along to the right? So we can do the rotation matrix of y by some little y, some infinitesimal small value. And you guys tell me what the matrix looks like.
1, 0, delta y. 0, 1, 0, 1, 0. 0. Negative delta y. 0, 1. Oh, yeah, 1, 0, 0, 0, 0.
You all see or know what got this? You just let him do the talking? The rest of you are all talked out, huh? Okay. And rotate Z. Somebody other than me. If no one else wants to talk to him? 1.
Negative delta z.
Negative delta Z.
0, 0. And delta z. 1, 0, 0, 0. 0, 0, 1, 0. 0, 0, 0, 1.
Come on, hold on. This is hard.
Your cosines are being value 1.
Small angle approximation. Some differential small value changes. So we're gonna carry the ones along for the ride. So basically, we can rotate in general, right? We have the idea of if we have a rotation by a little a, that's kind of the idea we've got, okay? That's the idea. So what happens when we rotate about some arbitrary point Q? Well, we're gonna rotate the motion about I, the motion about J, and the motion about K. Right, so we're saying if we want to find out some arbitrary d theta about Q, I already wrote that up, about Q, we can look at the rotations and their individual component contributions. So that's why we're saying the motion about I, the motion about J, the motion about K. Which we already know because this is the motion about X, right? So this is rot X by some little X. This is rot Y by some little Y. And this is rotation Z by some little Z, right? So that the rotation Q by some angle is going to be the rotation of X by little x. The rotation, and I'm multiplying them together because I've already separated them out, right? They're in an individual of Y delta Y, Z delta Z.
Is that wrong? Q.
Q. So we multiply them all together. So let's multiply all this matrix, this big matrix. So if you remember back, we had these together. So we're basically saying we're going to multiply this guy times this guy times this guy. I'll save you the hassle. Okay. I'm going to give you the resultants. So we're going to go 1. We have minus delta Z, a delta Y. We're going to get a delta X, delta Y. In fact, I'm going to give myself a little bit more room. Let's go minus delta Z and delta Y. Okay, so we have delta X, delta Y plus delta Z. And I'm going to have minus delta X, delta Y, delta Z plus 1 minus delta. This is minus delta Y plus delta X, delta Z, delta X plus delta Y, delta Z, 1. And then we're going to do 0, 0, 0, and do a 0, 0, 0, 1. There's no translation, but we're still going to, let's write that in. Now, can we do a better job with this? No. If I have a small value, times a very small value times a very small value, I have a very, very small value, yes? Plus a very small value. So I have a very, very small value. So very times very is a very, very, plus a very. I can basically ignore these and focus only on that one. Agreed? Now this is a very, very, very small value. So then I'm just going to say, all right, that's 0. We're going to keep the 1. A very small value and a very, very small value, that's a 0. A very small x and a very, very small xy, that goes to 0. So that cleans things up a little bit. In fact, if we look at this, I'm going to go ahead and just get rid of this for a moment, if that's okay with you guys. we can look at that as that would be a 0 minus delta z, delta y. Delta z is 0 minus delta y, delta x, and 0. We've seen that somewhere before? Did we just see this?
Yeah, that
Oh, that was
That's S, isn't it?
Yeah,
Ah,
skew matrix.
that's our skew matrix. I think. That's our S, right? Whoops, that's a really big S. That's S. And we can do one more thing we can add an I. We don't want the zeros there. Let's get rid of those zeros. So we're going to make an S plus I. You'll find out later why. So we're going to make this S plus I. And so let's go ahead and let's do an S plus I. And we're also going to make it into a 4x4. Okay, so this becomes 0, 0, 0, 1, 0, 0, 0. Fair? So this becomes our S matrix right here, our S plus I. So when we do that, we'll get a 1, a minus a z, a delta y, and then a 0. And we'll get a delta x, a 1, a minus delta x, a 0, a minus delta y, delta x, 0. No, that's a 1. That's a 0, and then I get a 0, 0, 0, 1. Where this submatrix is my S. Yeah, I should not use black on that bottom. That's my S plus. That's our arbitrary rotation about a point Q. Yeah, what he said. All right, so we're rotating. We're applying this rotational small. This is a differential motion. Differential, small little amount of motion of theta about some point Q. We good so far? So what we're looking at is the differential rotation of a frame. So the question is how do we apply, or how do we use to describe the rotation motion, the rotation motion of a frame? We're going to get a new frame location from a differential rotation of the frame. What do we mean by that? So the differential motion of a frame, what we really want is we want the differential rotation plus the differential translation, right? So far we've only talked about the rotation part. The translation is actually trivial, to be honest with you. So we can apply the differential motions of a frame to an existing frame. Okay. So if I have some frame T, and we want to update that frame, updates in quotes, this infinitesimal differential amount of frame is going to be our new location of our frame. So that frame T is updated by some very small differential dt. That's containing all the components that includes the rotations and the translations, we'll get to that one in a minute, of that frame. So far so good? So what we're really saying is we're between two frames T1, or we're between 2 times T1 and T2. That's our delta T, where delta T is very, 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 very small. So that our new frame location is nothing more than our old frame location plus some infinitesimal amount of dt. dt is a frame difference, or a frame differential. So we got to figure out how do we find dt. Now in calculus land, we take the derivative, we take the first derivative. But do we take the first derivative of a frame? How do we take the first derivative of the transform? Gradient. Have we already done it?
Simplifying by the deep parameter?
Well, let's think about it. My dt is a composition of translation and rotation, yes? And I can say that my translation rotation minus I, in fact, I can do this right here, right? So I've got dt is this differential motion times t, right? Some operation is going to take a differential on frame t to result in dt. And that differential motion operation is going to be a translate dx, dy, dz, and a rotation of some arbitrary point q d theta times t. I can factor out, subtract the I, that I can do right here. And put my t out here. But that, we've already done that, haven't we? That is, in fact, our S matrix. Our S matrix is the operation of the del operator, almost. So that our del operator matrix becomes 0. You should almost have this memorized by now. Z, y, and I can use a dx, delta x, 0, minus delta x, dy, minus delta y, delta x, 0, dz, 0, 0, 0. That matrix is an operator. I can take that matrix del and figure out what dt is given delta x, delta y, delta z, dx, dy, dz.
Professor, should that be 1 or 0?
Zeros.
Oh, 0.
Oh, on the bottom down here,
Okay.
I subtracted out the identity, it goes to 0.
Okay.
So that's what happened right there. So that's the idea. So dt is this, and so we actually define it. We're going to call it the delta operator matrix. So this matrix, it's the same as a transform when you think about how a transform worked on a point, except now this matrix is operating on another matrix. And that matrix, it's T, who happens to have both rotation and translation information embedded in. So far, so good? Kind of there, right? You're buying it. At least you're buying it, right? Kind of go back and read the book now, but you can read the book and understand it. You may have read the book, I don't understand.
Is it DC for the middle row? Fine.
That one?
No, for the middle up, like
Left.
one more up. Down.
I don't think so. No. Oh, this one right here?
Yeah.
Yeah, actually, yeah, thank you. Yeah, no, that's right. I have it wrong, I didn't understand it as we kept. Yeah, there is some symmetry, kind of. we call skew symmetric. I have it here, give me a go. Yeah, copy and paste that one. Okay.
And we don't have the bottom right one because of subtraction, we got rid of the corner right one.
Right, we subtracted I. So all the ones in the diagonal went bye-bye. Okay, so this is our delta matrix, our delta differential motion operator. Let's just go ahead and read that. And you saw how we derived it, right? How did we derive it? Because we went to this right over here, right? And we use our small angle identities. That's how we know it's a DZ, right? Here's your DZ. We use the small angle identities to get rid of the sines and cosines and to get rid of the products, resulting in this guy right here. So this is it. And so this is the differential operator. It is not a frame. But you can think about it. It is similar to how we define the transform. Any questions so far? You probably want to see an example at this point, right? Good. We have an example. Thank God. So what we're going to do is we're going to have a differential rotation of 0.1 radians per second. It's a rate, right? We're talking about rates. This is how fast something's rotating. We're going to rotate it about the y-axis, and we're going to translate along the x-axis and the z-axis. Given frame B of 0, 0, 1, 10, 1, 0, 0, 5, 0, 1, 0, 3, and then the 0, 0, 1 for free. Okay. We know that we can imagine how we got to the B from our DH parameters. Right? Rotations, given thetas, etc. But we're moving this time. We're moving by so much units per second and radians per second. It's just considered units per second. Don't worry about millimeters, meters, inches, whatever. We will be dealing in radians though for the angular representation. So how do we solve that problem? So we know, let's just go back, this guy right here, our dy is equal to 0.0. Our dx is right there. Our dz is right there. So that means our del x and our del z are both equal to 0. And that our dy. Everybody so far so good on that? So what I'm really constructing is my del operators, my del matrix. I simply, by inspection, construct that matrix. So my resulting one is going to be a 0, right? Because, again, let's go back to what we had. That's a 0, but let's go back. This guy here is a 0. This guy is 0.1. This guy is a 0. That's a 0. That's a 0.1. That's a 0. This guy was a 0.3 and 0.2, right? 0.3, 0, and 0.2. So we literally construct that matrix right there by inspection. So we're going to have 0, 0, 0.1. So that's my delta y. I'll come back and put a different color on there. And then I have a 0 point. Sorry, that was a 1. I could do my writing small one. I had a 0, 0, 0, and the dy was 0. My delta y was a minus 0.1, 0, 0. This is a 0.2, and then 0, 0, 0, 1. Take that back. That's easy. So this is my dx, my dy, sorry, my dz. This is delta y and delta. So my small amounts of B change, my dB, differential amount B, is going to be equaling to del, the del operator, operated upon B. We were already given B, so now we can just multiply the two together. And so when we do that, our differential amount of motion of B is going to be 0, 0.1, 0, 0.4, 0, 0, 0, 0, 0, 0, minus 0.1, minus 0.8, 0, 0, 0, 0. So my new, let's see what we have here. Yeah, 0.8. If you multiply out, that's what you get. The implications are that the change in frame B due to the rotational velocity and translation velocity. So if we consider this as a general purpose frame, we can have these relationships. And so hang on a second. Let me go back real quick. I can say that my B mu, I didn't have this slide in there, so I'm just adding this to it. My B new is going to be my B old plus my original B. I'm sorry, my dB. So this was my old value. This was this guy right here. So this is B old. Take that guy, and we add this to it to get our B new. Easy. And so the implications are that the change in B due to rotational velocity and translation velocity if we consider frame T is a general purpose frame, then dt is going to be this guy right here. So we have our NOA frames with the differential amounts about NX, about NY, about NZ, about NY, about OY, about AZ, AY, NZ, OZ, and AZ. Those are our T's. But we have that 0 down here. We just have these zeros carried along for
Professor, what's that right there? GP?
general purpose.
Oh.
General purpose frame. Is this any T, arbitrary T? And so that our new frame location, as I just kind of got done saying, is our T mu is going to be dt plus RT, so that our B nu would become this. Not so hard now, is it? Now, how does this relate back to Jacobian? We haven't quite gotten there yet, but you begin to see that path relationship, right? So we begin to see how the Jacobians relating this. The Jacobians actually become quite hard to find, as we find out. But what if we know everything except for the Jacobian? I can find the inverse Jacobian, and then take its inverse to find the Jacobian. It sounds backwards, doesn't it? That's right. So if I can define the velocities, then I can find the inverse Jacobian. If I can find my inverse Jacobian, I can find my Jacobian. If I can find my Jacobian, I can find my inverse kinematics. So we really had to go the roundabout way to get inverse kinematics, right? We had to talk about the velocity motion and how it's changing, but when we think about it, that's exactly what it is, isn't it? The frame does not magically teleport to here, does it? It has to translate, it has to rotate, it has to have a velocity that goes from here to here. And what's defining that? It's the Jacobian. But the Jacobian is driven by the differential motions, which include the differential rotations and the differential translations. Differential rotations we just derived through that S matrix, which was driven by R. We multiply all those contributions of all those differential motions to arrive at that delta operator matrix that we can apply to frame T, arbitrary T. In this case, B, right? So arbitrary T plus some differential T is going to give us our new T. So from my new B, my old B, from there we're going to find out when we come back from the break how we get to the Jacobian from there. Once I get the Jacobian, I can do my inverse kinematics. Now you see why I skipped on Jacobians and inverse kinematics, so we'll get back to it. Question?
So our rotational and translational differential motions are being represented by the inverse Jacobian. That inverse Jacobian can then be inverted to solve for the Jacobian, and that is our basis for inverse kinematics.
Yes.
Okay, that was it.
In a nutshell, yeah. All right, guys, that's all we got for this week. Great job in your presentation.